So we've seen the one nearest neighbor approach to the face recognition problem. So you have a new photo of one of the people that also appear in your training set, and your goal is to say which person is most likely in that photo out of the people who you have in your training set. So here what we have is a different approach to the same problem. So specifically for a training set where there are 6 people, so multiple photos for each person. And what this is one way to say it, the simplest possible neural network that you could have. So what this is it's a way to write down a computation. So I'll explain in a second what the computation is, right? So we have 4,096 inputs. So that's just because 4,096 is 64 times 64. This is how many inputs we have per image. So the individual pixels, 64 times 64, 4,096. So we plug in the first pixel in the image vector here, the second one here, the 30th one here, and so on. And then from those inputs, we compute the outputs. So the outputs are Z1 through Z6. So the way you compute Z1 is by multiplying each of the inputs by a weight. So each of those arrows here, those are usually called edges, is associated with a weight. So the weight here would be W111. So 1, you'll see why the 1 here is later. This one says it goes out from X1, and this one says it comes into Z1. And now this weight would be W112. So this one is always going to be here. This one says it goes out of X1. This 2 says it goes into Z2. So this one, for example, would be W4096, 6. Okay, so you have those weights. So they're just numbers, right? So now to compute ZK, for example, what you would do is you would say, okay, ZK is going to be B1K. So there's also a B here. So this is, for example, B14. And then you'll just add X1 times the associated weight, X2 times the associated weight, and so on. So it would be X1 times W11K, and then you'll add X2 times W, so the 1 is always there for those ones. Now it goes out of 2 and it goes into K. And so on up to X4096 times W1 4096 K, like this. And finally you apply the logistic function to it. So it's going to be like this. So the logistic function, you can see a graph of the logistic function over there. So the formula is, you've probably already seen it, is like this. So sigma of y is this. So you take this thing and you just pass it through here. Now, one thing to note about the logistic function is it's monotonically increasing, meaning that if this is larger, then sigma of this is also larger than it would be if this sum were smaller. Okay? So this you can write using sigma notation, right? So you can say B1K plus, and then you just go from J equals 1 to 4096. Xj, so like x1, x2, and so on, w1jk, like this. So another thing you could do is you could say, well, I'll take all of those w's and I'll take all the x's and I'll think of it as a dot product, right? So you can have a vector of the x's, so x1, x2, and so on up to x4096. And you can compute the dot product of that with W11K, W12K, and so on, up to W1 4096K. And you could just say this times this, plus this times this, plus this times this. That's exactly this sum, or this thing with the signal notation. So you can write it like that. And this thing we can write as W1 star K, with the star being kind of the wild card, right? So the star is like everything. So this thing is this. So in our previous notation, we can say that the theta in this case is W comma B, right? Why? Because the W and B, they determine how we take in the X and transform them into the Zs. So there is also a structure here, like those sums correspond to the structure, but what's changing, like what will change depending on what the training set is the W and the B. So the theta is all the W's, like all the W's here and the B.